So welcome all. Let's get started. Sumit, over to you.
Yeah, sure. Thanks, Vivek. I'll start a bit about my introduction. So, uh, I am currently working with a fintech firm, and I have say about 7 to 8 years of experience. That would be partly in computer vision, some of it in machine learning, and recently with the Gen AI part of the development. I've been in Pune since I think 4 years now. I've been in Bangalore, but I think Vivek, I couldn't meet you that time, probably 4 to 5 years back. Uh, I discovered this community a couple of years back, and yeah, as Vivek mentioned, it's really an excellent community for like-minded people like us who are interested in AI and the recent developments to keep track of. Right. So this is just one of an exercise to contribute to the community back. Right. And today I'll be talking more on the stuff about uh, this paper that was published. It was titled as Self-Discover, and Google recently published a blog post about this, which was LLMs self-discover reasoning structures. So I'll give you a bit of background to people who sort of do not have much basic about it, right? So as you know, LLMs are the recent buzz, considering the GPT models that have come up, and again the Gemini models which Google is launching, and there are many more models you might be hearing of, right? So the key to access these kind of condensed intelligence, so we call it as condensed intelligence because it has all of the worlds of it has the understanding of whole of the world condensed in a very small uh, small structure, basically, right? We call it as models, right? So the key to access these kind of models is prompt engineering. Now, prompt engineering comes in many shapes and sizes, and if you might have attended few webinars, particularly by Dolce, so she talked about different formats like graph prompting, chain of thoughts, and other webinars like this, right? So this webinar is going to be somewhat in that part of the prompt engineering, right? So we are trying to get maximum out of LLMs, and we are trying to engineer our prompt in that sense. Okay? Uh, so earlier, as you know, or if you have already used ChatGPT, you basically simply ask a question to ChatGPT with whatever understanding you have, and then it replies back. Now, one thing we noticed during an experiment is like whatever ChatGPT understand, and let's say whatever human understands. So let's say me as a human types a particular prompt inside that ChatGPT window. How much of it is exactly getting translated to ChatGPT? So we call one domain as a human plane, that is our understanding, right? That is a human plane of understanding, and another plane we call it as LLM plane of understanding. So the gap, how big is the gap, right? That is where multiple techniques have been researched to see what LLMs can understand. So let's take an example of, say, for example, chain of thought. So inside chain of thought, what you basically do is you represent, or you basically put your prompt in such a way that instead of just specifying the objective, you basically list out all the steps that you're thinking, right? If it is a mathematical problem, then maybe you tell the model that this is probably how you should approach your answer step by step, right? So again, self-discover was made in such a way that eventually whatever knowledge I shoot inside a prompt, right? I'm not sure if that is exactly the prompt I need to get the exact objective. But then what I would do is maybe I would have LLMs modify, or LLMs tackle this particular prompt and maybe modify it. So that is where the word comes self-discover, right? So that is whatever task intrinsic reasoning structures are there, or whatever task intrinsic prompt that the model has to generate, that LLM should already be able to figure out. Okay. So what this mechanism does is it basically, and I'll go through much details, but I'm giving a sort of high level overview. It basically has multiple modules, you can say. So as a human, if we think of a human intelligence, it's basically not just a language intelligence. Human have reasoning abilities. Human have basically verbal abilities, right? So if we try to divide human intelligence into multiple blocks, likewise, we have multiple modules that we show that, okay, these are the modules which I'm trying to use, and maybe this is the objective I want to solve using these modules. So as a human, maybe my understanding is this much. Let's try to do more refinement, or let's try to refine this such that the objective is sort of solved for in that case. And the researchers who published this paper, actually they experimented with GPT-4 and PaLM 2's performance. So I think at that time Gemini was not there, if I recall correctly. So the improvement they saw was for especially reasoning tasks, and the benchmarks that have been established, especially BigBench-Hard. So there they observed that 32% of improvement was observed as compared to chain of thought, which prompted me to sort of read through the paper, implement it, and see what's so new about this, right? Uh, with respect to there are multiple flavors of COT. So there is one flavor called as CoT-Self-Consistency, where it has outperformed on an average more than 20%, and it requires even fewer compute, fewer inference compute rather. Uh, yeah. So this is basically the diagram that they had published inside the paper itself. I'll work through these blocks one by one, and then probably move on to an elaborate example where we'll go through how this whole operation works here. Okay. So at the start, the first black box you see are the prerequisites needed. That is, obviously, you need a language model. Second is you need reasoning objects or reasoning colored objects. So basically, this brown box defines the objective that needs to be solved for. Say, for example, if I'm a Gen AI engineer and my job is to auto generate summary from a given headline, right? So the task would contain my objective. That is uh, typically how the prompt start is. You are, let's say, an analyst at a financial services firm. Your job is to go through the article and probably generate a 2 or 3 line summary. If you want, you can add a little bit more of objective, but I think for this example, this would work. So task means what is the exact objective that you want to do. And then the third block you see here is atomic reasoning modules. So these are basically just some natural language statements, or basically natural language paragraphs, which we call it as modules. And these modules represent some kind of intelligence. So one of them, let's say, could be a reasoning module, or maybe one of them could be a RCA, that is root cause analysis. So where we have just mentioned what is root cause analysis, that is whenever you are trying to solve a problem or trying to debug an error, basically you should always try to identify the root, which could lie maybe in this particular file or something like that, right? So these are the modules that can be tailored for your task. Say, for example, if I'm debugging a code, these modules can simply be natural language statements saying that maybe I just need to follow object-oriented fashion of programming, right? And then once we have this prerequisites, we send this to this self-discover framework. Okay. So what happens is self-discover frameworks, it does a couple of iterations with LLMs. It goes back and forth, and then it identifies out of the reasoning modules, and for this given task, in what way I can pick up the exact module, or maybe I can modify the exact module and create a reasoning structure, right? Such that this thing on the right side can be my new prompt. That is, this can be my final prompt here. Yeah. So this is on the basis of couple of iterations that happens inside this self-discover framework, and then out comes this whole reasoning structure. So this is how like the end-to-end workflow of the self-discover framework operates. Yeah. Yeah. There are few assumptions in this case. Like, for example, if you are trying to solve, let's say, a math problem, then inside the module, you have probably given uh, probably a different kind of module, right? So what you are asking LLM to do is, with the given set of tools, you need to solve this, right? So it assumes that whatever atomic reasoning module is there, the assumption is that these variables or these sort of modules will lead to the final answer. If the modules are not enough, or basically if the understanding is not enough, in that case it might happen that the output might not be exactly, or the performance might not be exactly what we exactly want here. So I'll go through a little bit of background here, especially with self-consistency COT, right? So if you remember if you remember the chain of thought prompting, so the idea here is that inside this prompt here, you specify maybe a few short examples here in this case. Like for example, yeah, if there are three cars in the parking lot and two more cars arrive, how many cars are there in the parking lot, right? So this is probably the way we would ask question to another human. Okay, but let's say if I want to solve a problem using LLM, one of the techniques that has worked, and you might also know, is a few shot, where we demonstrate that maybe approach this problem step by step, right? First, let us understand how many cars are there inside the parking lot. So we write this separate natural language statement in this case. So first statement reflects one fundamental understanding, that is there are three cars in the parking lot, right? Now there is another sentence which states an iterative understanding, that is upon, I mean, there were three and then two more arrived, and then now there are five cars in total, right? So this is how a human has answered five in this case. So if you see, this Q part is basically the task that LLM has to solve. A part, or the answer part, is more like a demonstration that we are showing to the particular LLM, saying that, okay, this is how maybe I would solve the problem, and maybe you can think of solving this as to. So there are multiple varieties of sort of COT that have been studied, and then we have seen that chain of thought promptings works quite well, and it actually quite works well in a lot of areas basically. So here again, they have shown few examples here, that is what path a language model can take, right, depending on how prompt is modified in this case. There are uh, few more prompting techniques, like least to most prompting techniques, which have also been studied, where the idea is that least indicates the least amount of decomposition that is needed for a prompt. So for example, in the previous example that we were looking at, that is the parking car examples, we identify how much decomposition or how much explanation is needed for a prompt. So that is called as a least prompting method. And most prompting is basically you sort of decompose the prompt to a level that you basically overkill it, right? So this has been studied quite a lot, where they have identified least to most prompting techniques as well. They keep on decomposing the whole problem into multiple sub problems. Now this also comes in line with the agents as well. So today's, if you see architectures that have been coming up, right? So we have specialized agents for specialized tasks. The idea is that we will decompose multiple, or basically one big problem, into few small problems, and then specify, or basically we will solve those sub problems, and then eventually that will lead us to an answer. Yeah, I'll pause. Maybe if anyone has any question.
So, folks, feel free to ask questions. It's pretty complex stuff on prompt engineering, and we are all still learning about prompt, creation and engineering.
Yeah, so can we go back to that slide, previous slide, where it was trying to find, not this one, previous one, please? Yeah, so here it was trying to find the answer, right? So What is the kind of sort of this three basically breakdown? And I see in the middle part the answer is wrong, but I don't know how this maths is doing right in the middle part. But what is the? I mean, is it? Uh, I mean, internally it is doing that. This kind of reasoning and coming out the answer.
Well, that's $1 million question. I mean, is it really doing that kind of reasoning? But yeah, I mean, to answer your question, attempts have been made to sort of look at what is the internal representation of LLMs when we typically ask this question, this type of questions, right? So here, like basically, they have just shown what all an multiple types of internal representation can lead to, right? I mean, if you basically elaborate a lot, probably it will go through this route. If you elaborate a little less, it will go through this route. So something like that. So this is just an example on how, I mean, COT works in multiple ways. Yeah.
Okay.
I mean, see, one of the frameworks, what it says is, if you basically give one prompt to a language model, it need not necessarily generate one particular answer. Maybe it can generate a multiple set of answers, right? And again, when we say it is generating multiple answers, the assumption is that it is probably thinking in multiple directions in that case. So what it is ultimately doing is that out of the whole thought process it is having, it may be samples of few set of reasoning paths as shown here, right? So these are the three reasoning paths it has selected. And then ultimately whatever answers are there. So one answer is 18, another is 26, and another is 18. So if I basically look like something like an ensemble voting, so that as per that, they have declared the answer is 18. So what ultimately they are doing is that there are multiple techniques in COT where you can track multiple reasoning paths, right? And then sort of aggregate these multiple answers to get a final answer, probably with max voting or something like that.
So Sumit, you are saying that the trick is in training LLMs on reasoning paths.
Can you repeat that question, Vic?
So you need to train the LLM on reasoning paths. But how did it apply these reasoning paths you are showing here?
Yeah. So this technique, which is called as self-consistency, so this self-consistency falls under a paradigm of COT actually.
Right.
So ultimately, under the self-consistency, you can generate multiple reasoning paths. I mean, that's sort of how the framework operates on, and this is considered as one of the best frameworks that is available with respect to COT. So that is what.
I will ask a naive question. How do you tell LLM to apply self-consistency versus chain of thought prompting? How do I tell LLM to apply self-consistency solution?
Yeah, that I'll have to get back on that. So exactly, I have not worked with self-consistency.
Okay.
Yeah.
Okay, fine.
Okay. So we'll move on to self-discover, and basically what is the fundamental understanding behind this self-discover, the rationale behind self-discover. Okay. So typically, like whenever we have a task, we send it as a concise prompt and we sort of generate an answer. So that's like a direct method of getting an answer, right? What chain of thought basically does is you have a task and then you generate a rationale behind that. That is maybe with respect to multiple steps or multiple prompts, you try to understand how much can LLM decompose and then try to solve one sub problem at a time, right? So that is what chain of thought is. Sorry. What self discover does is, if this is particular task, ultimately we will have I won't say trained reasoning structure, But the idea is to generate basically a reasoning structure which is very specific to a particular task. Okay, and then this reasoning structure is based on few modules that are already present at the backend of LLM. Once you have this, once you train a particular task specific reasoning structure, you generate a structured reasoning problem, and that is what you fire as a prompt to generate a particular answer. So I think I'll just go quickly to the modules which are there, which have been experimented in the paper. So if you see these modules which they are saying, these are basically just natural language statements. Okay, and they are, so how could I devise an experiment to solve a problem, or maybe how can I simplify the problem so that it is easier to solve. Okay, I'll go a little bit below. So let's read the 14th one, that is use risk analysis, evaluate potential risks, uncertainties, and trade-offs associated with different solutions or approaches to a particular problem. Emphasize assessing the potential consequences and likelihood of success and failure, and making informed decisions based on balance analysis of risks and benefits. Now, this is sort of a little trickier to understand. I mean, because the name is modules, but these seem to be very natural language sentences or paragraphs, right? So the idea here is that these 39 modules will be your sort of hands and legs. Uh, this is what LLM will eventually use to tune that particular, maybe a particular module. So one of the module here is critical thinking. It will try to use whichever modules here are applicable, and then finally generate an answer based on the tuned reasoning structure. Okay? So a quick look about how the modules will look like, right? And how I'll go to the part where we were talking about the flow here in this case. So the framework, which is self-discover, is listed all on the slide here. So it says that your first step is select. That is from all the seed modules that you have. So in our case, all the 39 modules you have. Basically, what you do is you basically send along with your task to the language model all the modules, right? And you say that, okay, I'm trying to solve this particular task. These are the modules I have, or basically this is the information I want to solve it with, right? What you need to do is you need to select the most important modules here in this case, right? So maybe, for example, in few problems, a risk analysis kind of module might be more important as compared to probably another module in this case, right? Or maybe a couple of modules might be more important as compared to other, right? So first step, we will select whichever modules are most important in this case, right? This is the first step. Once we have all the selected modules, we tell the model to adapt. What does adapt mean here in this case is, for all the selected modules, maybe it has selected 5 important or 10 important modules, it needs to adapt these modules in this case. That is, maybe fine tune it, maybe change the language of it, right? Uh, or maybe do some modification such that model says that probably, okay, this is the version of the prompt, or this is the version of the module you need to use, right? So the second step generates adapted modules in this case. And the third part is implement. So once you have some adapted modules here, these adapted modules will go to a language model, and it will say that, okay, based on this particular adapted module, maybe generate some sort of a reasoning structure. So in this paper, they have claimed that this final reasoning structure which they ask the model to generate, if it is typically generated in JSON, they got a kind of a performance boost there in that case. Although, like, for, I mean, simple discussion, obviously a reasoning structure can have probably any sort of structure, right? Maybe some sort of a if-else part of uh, if else kind of structure as well would have sufficed there, right? but they have claimed that this kind of JSON reasoning structure also does good for them, right? So ultimately, this is how the framework works. That is, once you have all the knowledge that you want to solve your problem with, instead of dumping that everything inside a prompt, do a couple of iterations to fine tune this, and then generate a reasoning structure. Now, the interesting part of the paper is that they did not share the implementation. So I think this is pretty much open to assumptions, basically. Like, for example, here when they have said that they are using a language model in this case, right, to adapt the module and how to use the ultimate reasoning structure. One can think of an agents as well. I mean, how to use agents in this particular flow, right? So the framework still works with agents, and we experimented this with a little bit of agentic workflow as well, right? But I'll stick to the paper today. Yeah. So again, yeah, this slide again demonstrates the same a little bit in detail. That is, the first part is select several reasoning modules that are crucial to utilize in order to solve the given task, right? So all the reasoning modules, that is critical thinking, step by step, propose and verify. So if someone has experimented extensively with COT, you might remember that you always specify in the prompt that always think in step by step, or probably propose your answer in step by step, like this. And then you can have multiple examples of each of the modules here as well, right? Adapt says that rephrase and specify each reasoning module so that it better helps solving the task. That is, for a critical thinking, maybe an elaborate string would help, or maybe a few examples would help. So here it rephrases the particular prompt structure. And then finally implement, that is, operationalize the reasoning modules into a step-by-step reasoning plan. That is, you have the modules, now you are representing it in a JSON structure, and then you are sending that as a prompt to your particular LLM in this case. Now, this particular adapt thing, we experimented this quite a lot. The reason being, so we were basically generating a simple summary from headline, and our problem statement was that we needed to generate a summary that is legally safe. So what do I mean by legally safe is I cannot use words at whim, or basically I cannot use something like an inflammatory words. So let us say if there was, and again, this is just a example. So if there was some incident at a car parking lot and probably a car was damaged, so I cannot say that maybe this particular company was responsible for a car damage, because again, legally that becomes an issue, saying that this is a claim by the company who is writing the headlines. So that sort of lands in legal trouble. So we had to basically we tried to use this sort of framework where our models were like, instead of using the words damaged, maybe used allegedly damaged, right? So where we are safeguarding ourselves from the legal guardrails in that case. A few of the models where maybe use passive voice to generate headlines, right? And whenever we implemented multiple modules as per our understanding, what we felt is that if we elaborate that particular module, or if we elaborate that particular rule, it always helped us implement, or it always helped us boost the performance, which indicated that the kind of language which we as humans speak is probably not the exact one which should be used in the prompt, right? I mean, the understanding of LLMs is in a different plane as compared to human. So that is why we found that this adapt framework turned out much better. It tried to elaborate the modules as quickly as possible, as wide as possible, covering multiple steps there. And specifying examples also helped fine tune this adapt module here in this case. That is fine tuning the whole rule here in this case. Yeah. So we'll just go through like a pseudocode sort of thing. Uh, how you can use the self-discover in your case as well, right? So it's a very simple thing. Like basically, this is your task. You're saying that Lisa has 10 examples. She gives 3 apples to her friend and then buys 5 more apples from the store. How many apples does Lisa have now? So one of the implementation I found, I don't remember the name exactly of this person, but he basically just implemented very plain Python code where it just said that this is basically the stage 1, and it passes all the reasoning modules along with the task example to the select block here. So I went and checked how exactly the select block was implemented here. So it was just more like a natural language formation saying that, these are the modules I want to work with. You need to fine tune this with the example listed below each of the rule. And then ultimately that is how they have implemented the select block here, and same for adapt and reasoning structure here in this case. In couple of implementations, I found that inside this adapt reasoning modules block, when they specified all the selected modules, along with that, they also specified the modules which were rejected by the select modules block here. The understanding being that they just fine tune whichever are most important, but keep the other rules unmodified, and then ultimately create a reasoning structure like this. Yeah. So I've included a GitHub link, and I'll anyway go through a quick code, which is by Llama Pack. So I think let me just.
So Sumit, one question here. I mean, if you go back to previous slide, so when we are seeing this, sort of select, adapt, and then sort of implement. So is that the sort of underlying kind of when you are sort of selecting these modules, right? So is it the orchestration library, and then PAL? There is one more, right? Program-aided library, right? So especially where reasoning comes in, so you have a PAL framework, right? Program-aided library, I believe, which helps basically to translate a reasoning statement to a Python code, basically, right? So do you know, is it, I mean, I'm just thinking from the prompt engineering and what you are kind of explaining here. So is this, when we are saying these modules, are these modules, I mean, what are these modules?
Yeah, so modules are basically just some, you can say, natural language statements. So this is basically like, let's just look at rule number 10 where it says critical thinking. Okay, so this is probably what I would have specified in a direct prompt. Maybe use critical thinking. This is what critical thinking is, something like that. So modules are basically just some natural language instructions that need to be looked at for solving the task. So they're just plain natural language statements. I mean, yeah.
So basically, these modules, I mean, when we are programming, we need to construct these modules. I mean, we can construct our own modules.
Exactly. Yes.
Okay. And then it will select, I mean, which modules you are parsing, basically. I mean, in the code you are showing, right?
Yes. Yes.
Okay. All right. So maybe I think underlying sort of when LLM takes it up, so there is a orchestration library, there is a PAL, probably
Yeah.
that's
Exactly.
the under the bonnet or under the hood, right? So
Yeah.
that must be
Exactly.
translating this your modules.
Yeah, I'm not sure about translation, but there is an orchestration part of inside Python itself. So basically, what I saw is it uses typically 4 to 5 LLM calls, and it essentially just does this. Like it collects your task objective, and it collects your 39 reasoning models, and then it makes a call to LLM with the exact prompt. That is, these are the modules I want to solve my problem with. Select the most important ones or most relevant ones, right? So your LLM returns probably just 1, 2, 3, whichever are the most important. So that is how this is working right now.
Yeah, so there is a orchestration library underneath
Yeah.
LLM, so it must be using that to kind of orchestrate this, whatever the modules we are passing.
Yes, yes.
Okay, thank you.
Right. So there are 3 slides I have which sort of give a deeper explanation of how the framework works. Like for example, in the first stage, what it does is we are trying to ask how can I break down this problem into smaller, more manageable parts, right? And LLM basically returns that this is how you can decompose the problem. Probably you need to track how many apples we already have, how many apples are new, something like that. And then it says that another module which says that there is a critical thinking, right? So this critical thinking are very relevant to reasoning modules. Since this is a reasoning problem, 9 and 10, these 2 parts are more important to solve the problem here in this case. Then the part of second is adapting, or basically fine-tuning your rules in this case. This adapting involves, that is, breaking down your problem one by one. That is, first what your rule says is how can I break down this problem into smaller, more manageable parts. Now it tries to solve using this particular instruction. That is, break down the problem, calculate how many apples Lisa has after giving 3 to her friend, then do this, do that. And here it states that by breaking down the problem into these smaller tasks, it becomes easier to solve, right? And along with the first module that has been applied, after that, second module is applied, which says critical thinking. So it uses the information under this block, critical thinking, and then tries to answer what all it can come up with, right? After implementing and selecting, so we saw the select and adapt block. Now it tries to implement a reasoning structure here in this case. So first is basically it tries to come up with a structure, that is, calculate how many apples Lisa has after giving 3 to her friend. So this is basically one sort of structure it is trying to form. It is trying to form multiple blocks by which we can create a structure and we can use the structure again. So it does it for all the selected modules here. It does it for first module, that is breaking down the problem. It does it for critical thinking, right? And by the way, this is not the exact natural language output that comes out. So this is just an example described in detail. Okay? And ultimately, once it does this, it comes on to a final output saying that probably after implementing all the adapted modules, I can get a final answer now. So I'll quickly move to the Llama pack code which I have. That might decrease your confusion. Right? Yeah. Okay. So if you have,
possible,
yeah.
Sumeet, you can change the background. I mean, it's black and it's not able to, not readable actually. Yeah, that's better, I think now.
Okay.
Changes
I'll
the
just
front.
zoom in a bit. Yeah.
Thank you.
So I tried to see, I mean, if there was any way the publishers shared this approach, but I did not come up with a lot of approach. I think there was one implemented by inside a Llama pack. So this is the code where it is sort of much quicker to start with, and it is consistent with few other examples that I saw on the internet, right? So for implementing this, you will basically need to install Llama embeddings, Llama index, and few other packages along with that. So Llama index LLMs, Llama index embeddings. So here I have, I don't know, I imported Azure AI embedding, but yeah, I have used Azure OpenAI service for this. So here we have We experimented with actually GPT-4, GPT 3.5. GPT-4 was not there at that time, I think. Yeah, so there is a llama pack by the name self-discover pack itself, right? So the command to download this is download llama pack. You just need to specify a folder where it will download the llama pack. Okay, and ultimately when you execute this code, it will come up with a nice folder there. Self-discover pack. Yeah. So this is a folder which comes after downloading that. Inside this, inside a llama index packs, you will find a base.py, and this is where you will see the reasoning models I was talking about. Okay. So these are, as you see, just natural language statements, right? And multiple. So here they have listed what 39 of them, right? So all of them just as simple as natural language statement, right? I tried to look, I mean, if there was more meaning to module when they were saying modules in the paper, but I did not find much about that. This is the closest one which I found where they have listed some examples there. Okay? And ultimately, this is your, so basically task. Right? Michael has 15 oranges. He gives 4 oranges to his brothers and trades 3 oranges. And later in the day, he realizes some of the oranges are spoiled, so he discards 2 of them. And then ultimately, the final statement, that is, if Michael decides to give 2 apples to his friend, how many oranges and apples does Michael have now? Okay. And then you have, you just run a self-discover pack over it. So inside this log, if you see, it basically runs one module here. That is, this is your task. And the first, and these are your basically multiple modules here. So first job is select prompt template, that is list down what all reasoning modules are relevant for it. Then you send that call to LLM. LLM basically returns some kind of some sort of modules which are very relevant, which you can see in the adapt template. That is module number 2 and module number 4 has been written, and there might be few more modules, right? So ultimately, this is just a call to LLM saying that this is the knowledge I have. Let me know which of them is relevant and which of them is noise here in this case. Right? Once you run an adapt LLM module on top of it, by the way, this is all the internal orchestration, right? I'm just explaining the logs, what is happening here. Once you adapt this, basically you modify your final module here in this case and generate a reasoning structure here in this case. So if we see the output that is generated here, it generates a very nice elaborate output with an explanation. That is, Michael initially has 15 oranges and 0 apples. Then it tries to track each of the events that is happening here one by one, and ultimately it says that reviewing the calculations, all transactions have been accounted for. Final counts are accurate. Here it declares the answer. Michael has 18 oranges and 9 apples. Typically for reasoning task, we observed that this particular framework was pretty much more consistent as compared to the other COT frameworks which we experimented inside internally. So this is again, yeah, one more similar example, but I think you get the final idea. Ultimately, it is just asking more LLM, more and more to LLMs, but again, it is just trying to solve one sub problem at a time, right? And then apart from just trying to solve the problem, along the way, it is also modifying the information that needs to be sent to LLM in this case. To a scrollable element, this is the final answer we get here in this case. So it really does a nice, reasoning structure, how it has come to the final answer. It lists down step by steps how it has come up with this kind of answer, right? Yeah, that is really it. This package is, by the way, available with the llama pack. So yeah, feel free to sort of download this and get quickly started and experimenting this. So it makes 3 LLM calls. That is what I saw. So one of our production strategies was basically, instead of using GPT-4, which is a little costlier than GPT 3.5, why not go to GPT 3.5 and hit 3 prompts? Because typically the problems we tried to solve were not much complex. So instead of spending $1 on GPT-4, let's just spend $0.2 for each iteration. So that is $0.6 to get one particular answer in this case, right? Which was cost-effective strategy in our case. Right? Yeah. So yes. Here they have basically used a couple of strategies to demonstrate how it generates a reasoning structure. And I tried to print this kind of JSON structure, but I haven't been able to yet. So when we try to apply CoT for this particular problem, and so they have tried to apply this multiple strategies: CoT, plan and solve, and self-reasoning. So they mentioned few complex reasoning problems where self-discover has performed good as compared to plan and solve and CoT. And then this is how they're demonstrating the reasoning structure looks like. That is, I think they are trying to identify some kind of shape, that if it is circle, heptagon, hexagon, etc. Right? And then they try to look this one step at a time after forming the reasoning structure here. And then they finally generate a final answer. Right. These are the numbers which they have reported. Few of the tasks on which they have run across multiple categories. So in all of them, CoT, self-discover over direct and self-discover over CoT. So this is sort of the performance improvement over direct prompting strategies and CoT. And again, I think they have also mentioned the evaluations on BigBench-Hard evaluation framework here in this case. So with GPT-4 and PaLM2L in this case as well. So I mean, nothing much to look here. I mean, this framework sort of comes out as an obvious winner as compared to other prompting strategies, is what they are saying. Now, one thing we looked at is basically what working with LLMs is pretty costly. Like basically, iterating over to find the optimal prompt is really costly, because let us say if you're trying to do some sort of experiment and you just hit 500 calls to LLMs. So if your prompt size is, let's say, around 32K and you're using something like GPT-4 32K problem, right? GPT-4 32K model. So your cost directly comes around somewhere around as good as $1 per prompt. And again, I'm just talking about the input cost. There is a separate output cost that comes out. So whatever output is generated, whatever tokens are generated, that also bears a cost. So I'm just assuming if we have something like a summary generation problem, so summary does not probably have much tokens in that case in the output, right? So even your input cost might range from somewhere around $300 to $500, right? So just for iteration, sometimes prompting experiments can take a lot of time, and again, finding the optimal prompt is really costly operation. So we tried to use this framework with very lightweight models. So I think we stuck to GPT 3.5 as far as I remember. And ultimately, what prompt that was generated out of the self-discover framework, we tried to use that over multiple models, 3.5, 4, and 4.0 we did not experiment. We experimented with a bit of Gemini. So we found that using the optimal prompts, even if we varied the model, the performance did not affect much, which indicated that for our sort of problem, basically it was not much complex problems to start with, and much of the intelligence or much of the fine tuning which we needed was inside the prompt itself. So the idea was that once we refine this prompt structure, we take it forward to all the problems that we want to solve. So this is, sort of like a supervised learning approach where you are sending out multiple examples, generating multiple reasoning structures, right? And then based on the reasoning structure, you are generating a new prompt here. So this is sort of like in a way, a supervised learning approach, I would say, but not exactly a supervised learning problem here. Uh, and we have found that typically in case of reasoning, or basically in the problems which typically require more like a sequential processing, where you have to decompose this complex problem into multiple sub problems, that is where the strategy really comes and really outperforms the other prompting strategies. Yeah, right? And yeah, this is basically just the summary, just a summary block diagram of it. I'll pause for any questions.
Yes, I have one.
Yeah.
So, can you do all of this in one single prompt since we have very large context windows nowadays? So,
Uh, we try to experiment that as well, but uh, we have the performance number actually, like around, if we do this in a single prompt. First of all, there is no sequential orchestration that happens with a single prompt. Like basically, even if you specify to divide this problem into multiple steps, right? So there is nothing that the model can learn out of the mistakes, or probably out of maybe the intermediate intermediate representation that comes out. And second thing is, if we try to combine everything inside one single prompt, that is what COT also does. So what COT does is basically a way of writing a COT prompt is, let me use a critical thinking module, and maybe I can use a little bit of explanation of critical thinking and maybe an elaborate example on how me as a human can decompose this into multiple problems, right? So that is how the COT strategy works here. What is lacking here, and what works for self-discover is, at every step LLM sends you an output back saying that, okay, this might work, this might not work, and that is probably why we have seen that self-discover works better as compared to a whole direct prompt strategy.
okay.
So I had a question. The the pack which is at the Llama pack, right? The self-discover. So most of the once you use that is when the self-discover thing starts working, is it?
Can you please repeat that question? I did not get that.
No, what I meant is like, suppose when you have to use the you have to use it in the Llama pack, right?
Yeah.
Okay, and then so the most of the thinking, I mean, like if you don't use, like most of the thinking, everything comes from the Llama pack itself, like the pack that you use in it, correct?
Okay. Yeah, I got the question. Yeah. So yes, I mean, if you just use Llama pack out of the box, you will have to use what is already written inside the Llama pack. Two things you can modify. One is your reasoning modules you can modify, and second part is actually you can do a bit of code changes there as well. So the let's say the first part where it says that it is trying to select, where is that? Yeah, select prompt. So basically, out of all the reasoning modules, all it is doing is it is just asking LLM to select which modules are relevant. So you can tweak that to your own explanation, to your own benefit. So you can elaborate it, right, saying that what kind of basically modules are those, which module can be useful in which situation. So ultimately, all your natural language information is going to go to LLM. So yeah, Llama pack, you can do a little bit of tweaking there, and then you can use it to your benefit. But if you are trying to use Llama pack out of the box, yeah, that is what you'll have to use.
Okay, good stuff. Any other questions, folks? So, Sumit, in the code, you are showing some API, sentence pack, that reasoning pack and all we have to import, right?
Yeah.
If we don't have those, using our own programmatically, we cannot implement the reasoning structures in our prompts or agentic workflow.
Yeah, I mean, the final output that we get, the final module that is there, which is reasoning LLM, it gives you a nice sort of JSON structure. It does give you that, but the kind of reasoning structure which they have described. So if you see this diagram, they have a nice nested JSON structure which says that, I mean, they are also capturing the hierarchy of information there. So I couldn't find that sort of information coming out of the Llama pack implementation there. So it just had this a single JSON, so one level JSON you can say, where all the modules were there. I couldn't come up with a nested one. So that is what I meant when I was saying about the limited implementation of Llama pack. Yeah.
In the code, can you show the call to LLM?
Yeah.
Where the LLM
Actually,
is invoked or called?
yeah. So it is not exactly clear. I mean, so this is an LLM object I create where I create a
Oh.
GPT-4 32K. So
Okay,
this is the configuration I have, and under somewhere I need to tie it to here. So self-discover
dot
pack.
run. You have dot run below in the next block. You have
Yeah,
dot
yeah.
run.
So I
So
create
dot
an
run
instance
runs
here
it.
where I tie LLM, and then dot run basically does your LLM calls here.
So these are some packaged pack
Yeah.
which adds certain process workflow. Okay.
Yes.
It's not a direct, GPT API call or Llama call to the LLM. So there are some packaging of things going on here using the
Yes.
pack concept. Okay. Okay, audience, any other questions?
So self-discover is the module, and run is the command within the self-discover module that you can use for the task, right? So
Yeah. So self-discover is your class basically. So this command
class.
instantiates your class.
Yes.
And here you basically send your LLM as an argument. So here you instantiate
So
an
the
object.
arguments for a self-discover class is the LLM model. One of the argument is the LLM model, right?
Yeah.
And as you go down, one of the like run is the what is that? A module inside the self-discover pack.
Yeah. So run is basically the method attached to this object.
Method attached to the class, right? So run is the method, and then your task is the task is what have you defined task as?
Yeah, task is
Okay.
you want to
Right.
solve.
Yeah, the prompt. Okay, so you're passing the prompt, and okay, calling. Okay.
Yeah. So you can actually really use this task here, because let's say, for example, you can use, if you're using an LLM with a very wider context window.
Okay.
So we specified a few examples or if you know, dynamic few shot strategy. So ultimately, you can basically just implement few examples here, saying that this is how a human would implement the task. And you can send it in the task here itself. So that also does, I mean, a little bit of performance improvement there.
Okay. So task is an argument within the method of the class self-discover pack, right?
Yeah. Task here, it would be an argument for this
argument for the method inside the class self-discover pack. Okay.
Yeah.
Now, how would I implement it for, let's say, GPT or Anthropic Claude? This is for Llama, right?
Yeah. So I mean, here I have seen that works with Azure OpenAI package. So there are a few extensions in Llama for Anthropic and Anthropic Claude as well. So probably, I mean, you would just have to import the right modules and declare your LLM object here.
Got it. Here you are deciding which LLM gets called. Okay.
Yeah. So Llama pack, Llama index. I mean, if someone is already working on LLMs, right? They might be aware. And these LLMs that are coming out, they already have this nice quick extensions to just plug in your model and maybe change it. So as you can see inside this Azure OpenAI, if I just change the names, GPT-4, 32K. So these many models are there for GPT. I just came to know now, but I can just
Llama index orchestration architecture essentially.
exactly.
Within Llama
Yes.
index, packs have been built for self-discover. Okay.
Exactly. Yeah.
Is Azure OpenAI anyway related to the Microsoft Azure platform, or like is it just named that way?
No, it's actually Microsoft Azure. We
Okay,
are
so
using an instance created on Azure.
okay, so Azure OpenAI is like an instance created by Microsoft, which you can be importing through Llama, from Llama, right? Like
Yeah, I mean, like see, OpenAI, whatever
so say if you
models
want
are
to
there.
Anthropic AI, so how do we do that?
Yeah, so there, I think you would have to use just the OpenAI package. So here I am using Azure OpenAI. So
Okay.
there would be another package with just OpenAI, and
Okay.
there you
With the
can
class
specify
Azure
your.
OpenAI, you're importing the module Azure OpenAI. You don't have. Should you call the class Azure OpenAI to import the module Azure, because I see it written twice over there, right? Azure OpenAI dot Azure OpenAI import Azure OpenAI. Yeah.
Yeah. So this is the file name where the code is stored,
Yeah.
and this is the class name.
Okay.
Yeah. So this basically has all the Azure settings here. So it just says that
Okay.
for
So you're
if you
importing
want
the
to use Azure OpenAI, it has your model has to be deployed inside Azure first, and it's not exactly like OpenAI. So OpenAI, a different module you can different package you can use for that case. So my deployments are on Azure. That's why I'm using this Azure OpenAI package.
Makes sense.
Can you go to the code where it ran the pack?
Yeah.
So it took 1 minute and 22 seconds, right, to do the entire thing.
Yeah.
So yeah, in your real world use case, did you find the latency a problem? If yes, how did you solve it?
Yeah. So we use this. We use this trick in two ways. Actually, we generated answers for 20 or 30 of the tasks, and finally, whatever the JSON structure we got, we tried to look which of the rules were consistent to solve the tasks here. So that was more like you can say an ensemble of reasoning structures what we have, right? And once we have that final reasoning structure, I don't need to run this self-discover pack in this case, right? Because ultimately, I want to solve multiple problems with a consistent reasoning structure. So my exercise here was just to get that reasoning structure here. And once I get the reasoning structure, I can then use a direct prompt strategy as well. Did that make sense?
Yes. Yeah. So all these techniques, they have a lot of latency. So that is the reason I'm always worried about. So yeah.
So how much it has dependency to the LLM, the version of LLM?
How much is the dependency of this framework on the LLM you're saying?
Versions, yeah. LLM,
Yeah.
undergoing changes, right? So a new version comes.
Yeah.
So this, framework also need to do something, or?
Yeah, I mean, for if you want to use this Llama pack, you will have to check basically what kind of LLMs are supported inside this LLMs module. But let's say tomorrow something like, I mean, again, just just for example, if GPT-5 comes and you want to use that, so probably either Llama Index needs to quickly release something here inside GPT-5, or maybe you need to take up the source code from this Llama Index and then implement yourself. But yeah, for the versions which we already have, like let's say GPT-4, GPT 3.5, or maybe Gemini, so support is already there. I mean, you just change the model name and it works quickly there. Yeah.
But the framework has to change, right?
Framework would remain the same.
Because
one can argue that the performance might change.
Yeah, see some of the latest GPT models, right? They may be already having this reasoning capability in the future, right? It's possibility, right?
Yeah. Newer GPT models they have more intelligence benchmarks, you can say, definitely. Yeah. So I mean, see, it's about experimentation. Like for example, if you obviously you will go with the direct prompting strategy first when you're trying to solve the problem. If that does not work, then the prompt engineering comes into the picture, where you would explore techniques like CoT and other stuff. This is where this particular framework falls in. So yeah, I mean, ideally, if really good models come out, we might not need this whole frameworks in its entirety. But then again, there have been a lot of reasoning problems where LLMs till today struggle. So yeah.
Okay. So if it is a framework where you can, like a generalized benchmarking where you can identify where the, you have a set of questions and then any new model comes, right? You can see whether that still applies. That is possible, right?
Yeah, I mean, it's there in one of the slide as well. Yeah. So this is one of the framework where they typically evaluate how intelligent the model is. And if you see, like, let's say, for example, let's assume GPT-4 is probably the best model. Let's just assume for an example. So for this particular task, it comes on to a score of 73 for the Boolean expressions part. If you use the same GPT-4 model with this self-discover framework, the performance shoots to 85. So yeah, I mean, 73, which is actually very comparable to a human average, is appreciable, obviously. But then with the production kind of accuracy, you may need to sort of push that accuracy to a little bit, and where this frameworks might come handy.
Okay, thank you. Yeah.
Okay, thanks, Sumit. Excellent webinar. Thank you, audience, for joining. I think the paper link has been shared in the chat, and reach out to us if you want to collaborate with us on AI or Gen AI disruption. I am putting my number here in the chat. So we are always looking for good contributors for our product division, and also research and webinar activities. So thank you all for joining. Thanks a lot, Sumit. Very nice session. Look forward to future such sessions from you as well.
Thank you, Vivek. Thank you for the opportunity.
Thank you, Sumeet.